I hope everybody is fine. And today I'm going to talk about, I'll go into some examples of evaluating some problems based on eigenvalue and eigenfunctions. And we'll do it in the context of Hilbert's space. And what we understand is that this Hilbert space is basically it's a complete inner product space, and what it means that it's a vector space. This Hilbert space is a vector space which is equipped with an inner product that's complete with respect to the norm induced by the inner product. So that is that's the precise definition of the Hilbert space. And in this video, we will be talking about we'll be discussing basically the eigenvalues and eigenfunctions in the context of Hilbert space. And in the context of this Hilbert space, an eigenvalue and the eigenfunctions they relate to linear operators. If I talk about the eigenfunction, suppose I take eigenfunction and assuming phi to be a non-zero vector in the Hilbert space, and and assuming this phi to be a non-zero vector in the Hilbert space, this non-zero vector phi in the Hilbert space is called eigenfunction of the linear operator. Let's choose that linear operator, say linear operator T. If there exists a scalar, so there should exist a scalar, assuming that scalar to be lambda. This lambda is what we call as eigenvalue. So we have a linear operator T acting on phi, which is a vector in a Hilbert space, leading to lambda phi. Here, this lambda is a scalar, and phi is the corresponding eigenfunction. And the scalar lambda that we have here, this lambda is called eigenvalue, and this eigenvalue is associated with the eigenfunction phi. And then comes the finding of the eigenvalues and eigenfunctions, and to find the eigenvalues and eigenfunctions of this linear operator, which I have chosen here, linear operator as T, we can solve the eigenvalue equation T phi equal to lambda phi. So this is our eigenvalue equation. Now, this thing can be rewritten in terms of differential equation. You can have a differential equation, or we can write it in terms of matrix equation. Depending on the context, depending on the beam of the problem that's under consideration. Say, if I take an example of quantum mechanics, we can make use of this eigenvalue equation to have the calculations on the system, and we can use differential equations, and this T might be a differential operator, and this T might be it might be a matrix having some elements with it. Now, to take on this discussion, we will choose a couple of problems so that the concept is clear. So the first problem that I would like to discuss here is I have T a linear operator, a differential operator in the Hilbert space, and this t of phi of x is minus double derivative of this phi. So what we have to find is we have to find the eigenvalue, and we will be finding the eigenvalues and eigenfunctions of t under the boundary conditions. This phi of 0 is equal to phi of pi is equal to 0. So this is the problem in the context, and we would like to solve this problem for eigenvalues and eigenfunctions. I think I have wrongly written here eigenvalues 2 times. This must be eigenfunction. So what should we do? We should write down this. This equation, this differential equation. So let us solve this this problem. So what we have minus d2 phi by dx2 equals lambda phi. So we can write down d2 phi by dx2 is minus lambda phi. We can do that. Now let us assume the solution of this differential equation of the form phi of x equals a sine of kx plus b cos of kx. And we can substitute this proposed solution in the differential equation here, and we can solve it. We will take the first derivative, will give us sine will become cos, so k will come out, and cos will become minus sine, and k will come out here. All right, that will be the case. And then we will have another derivative. So for another derivative, we will have another k out. So we will have k squared in both of these. This will come back to sine, and this will come back to cos. That is clear. That should be clear to everybody. So we can write down, differentiating. So we are basically taking double derivative of this equation, and what we will be left with is minus k squared times sine of kx, then plus, here it must be a, b cos of kx, and close it. Right, so what we have obtained here is this lambda. So what is lambda? Because this is again phi, so we can think of writing this as, it has to be minus k squared phi. So this lambda is nothing but k squared. So we can write down that lambda is k squared. Now what should we do? We should applying boundary conditions. We have the equation, right? What we have phi of x equal to a sine of kx plus b of cos kx. So at x equal to 0, phi of 0 will give us a sine 0 plus b. So this is b equal to 0. And at x is equal to pi, so we will have phi of pi. Okay, so that's going to give us a sine of, instead of x I have pi, this is k pi is equal to 0. So sine of k pi, so a is not equal to 0 here. So what that implies? That implies sine of k pi is 0. And for non-trivial solution, this sine of k pi is equal to 0. So we can write sine of k pi is sine of n pi. So sine will go, pi will go, so k will be n. So we have got the eigenvalues. So what are our eigenvalues then? Our eigenvalues are, so for k equal to n, so lambda is equal to k squared, but k is n, and this is going to give me the eigenvalues. So what are the eigenvalues? Lambda will be n squared. Right, so this is eigenvalue. So if I have the eigenvalue, now I can write down the eigenfunction. So this is my eigenvalues. Now I can write down eigenfunction. So what will be eigenfunction? That will be phi n of x equals a n of sine of, instead of k, this is nx. So this is going to be my eigenfunction with the eigenvalue lambda equal to n squared. And we can calculate this an using normalization. And we will get the eigenfunction phi n of x is under root of 2 by pi sine of nx. This is our eigenfunction, and eigenvalues, that will be lambda n is n squared, and n is the integral number, and it's equal to 1, 2, 3, and so on and so forth. So these will give us the values, the eigenvalues of solving this problem. Now let's take another problem. Let's have this problem where we will take the matrix formulation. T is a linear operator. It's a self-adjoint operator. Let me assume this T is a self-adjoint operator, and on a Hilbert space H, this H is the representative of Hilbert space. We should not be confused with this H as Hamiltonian, with the matrix representation of this T as T within the parenthesis. In standard basis, this T matrix is 2, 1, 1, and 2. Now, what we have to do is we want to calculate the eigenvalue and eigenvectors of this problem, of this matrix problem. So what we have T, a self-adjoint operator on a Hilbert space H. So we can start with the characteristic polynomial for this. If we have to calculate the eigenvalues, we can start with, in solving this problem, what we will do is we will take the determinant of T minus lambda I. So I is the identity matrix, and so when we write down the determinant of, so what we have to write down is the determinant of T minus lambda I. So what will be that? That will be determinant. Okay, so 2 minus lambda. So here we will have 2 minus lambda. Then I will have 1 here. Then I will have 1 here again, and then I will have 2 minus lambda here. So now we can solve this determinant, and this determinant has to be equal to 0. So if we solve this, so this will be 2 minus lambda whole square, then minus 1 so 1 equals 0. So this is going to give us lambda square minus 4 lambda plus 2 to the 4 minus 1 will give me 3 equal to 0. So we can solve this quadratic equation and we can find the roots. So solving this will give us lambda is minus b, that is 4 plus minus under root of b square will give me 16 minus 4 times 1 times 3, that's 12, divide by 2a, that's 2. So this will be 4 plus minus 2 by 2. So either lambda will be 6 by 2 or it will be 2 by 2. So I will have lambda 1 equal to 3, say, for example, and lambda 2 equal to 1. Now let's go with lambda 1. So we will use this lambda 1 equal to 3 in our equation. So what's the equation? The equation is that is for lambda 1 equal to 3, we have t minus 3i. All right, so t we know. So for lambda 1 we will be using here the value of lambda 1 equal to 3. So what we will get, this is 3 minus 2. This will give me minus 1, 1, 1, and minus 1. All right, and I can solve it now. I can solve it for t minus 3i times x and y equals 0, 0. So t minus 3i is minus 1, 1, 1 minus 1 times xy equals 0, 0. That should be the case. So this will yield us simply x equal to y. So our eigenvectors will be a column vector of 1 and 1. Now the same thing we will do for lambda 1 equal to lambda 2 equal to 1. Okay, so taking lambda 2 equal to 1 in the same problem, so what we will be left with is we will have t minus I times x and y equals 0 and 0. So t minus I will be 1, 1, 1, 1 times xy equals 0 and 0. And we can solve this, and after solving we will get this x will come out to be minus y. So we will have the eigenvectors as 1 and minus 1 for this problem. And lambda 1 and lambda 2, they are the eigenvalues, and we have the corresponding eigenvectors. For lambda 1 equal to 3, and for lambda 2 equal to 1, we have 1 and minus 1. So this is another problem. Now let's take another problem to solve.